My name's Jonathan Reichhold. I'm with Twitter. I've been there since about 2009. And what I'm going to talk to you today is about scaling Twitter to go after the fail whale. Big sounding title, but really how do we change Twitter and how it actually worked to actually, and as an organization, go after the fail whale itself instead of accepting it as a condition that was just normal. Brief history. Interesting to have Gene Kranz present this morning. I actually have done that job for Blue Origin, so it was kind of interesting to hear him talk about what it was like back at NASA when the science was way earlier in the game, I shall say, and without computers to do the trajectories. That's kind of interesting to hear just the things that they would come up with to do. I also designed airplanes and tested them, so I've done a little bit of high crisis type stuff over the years, and appreciate Gene coming and giving that presentation. Oh, come on. Okay, so early Twitter, we all know it. We were known for this fail whale. It came, it was kind of a fact of life for us. It basically, the fail whale was, you know, got a cutesy little graphic. People thought it was nice and pretty, but the truth is that that fail whale was what we were known for many years. Like people would say, oh, it's just a fail whale. So how do you get past that? How do you change it from being something that this is just normal to something that we actually can move forward from? And so to frame this, we're going to start talking about the 2010 World Cup. It's somewhat appropriate because the 2014 World Cup's coming up right behind it. And for Twitter, we went into this saying, you know, this will be an event, it'll have some traffic. We predicted what it would be based on everything we'd seen in the past, and we were completely and utterly wrong. We predicted a certain level of load that was not even close to what we saw in these games. And part of it is it's a world event. It's something where the whole world is talking about this game, and it's not just one country, it's not just one region of one country, it is the whole world. And for us, that was interesting because our tweets were growing a lot, the users were growing a lot, which is a great problem to have. But how do you go from like something where, you know, you think you're at the edges, you're pushing all these boundaries, and then add exponentially more load onto it at the same time that, you know, all of the systems are trying to come online? To say that it was a bit of a challenge is putting it nicely. And so to give you an idea of what we mean by load, so before this game started, we were seeing on the order of about 300 tweets a second at peaks. And during the games, we started seeing 3,200, 3,400 tweets a second, with every goal being scored, a red card or penalty or, you know, just stupid thing going on in the game. People would yell at each other. They used Twitter as basically their chat room for all intents and purposes. And we would see these huge conversations going on all over the world in every single game. And the interesting thing about the World Cup, and let's say this, was that it presents multiple games over a single day. So you'd be watching this game and it's like, okay, you survived that one. Well, then you got another one an hour and a half later, and then another one. There was, especially the early rounds, there's multiple periods in the day and there's multiple games during the day. So you get to see, you know, what's going on. And we were failing a lot. I will say that when the games first started, we thought we were going to be able to handle it, and we learned we were not ready. And part of what we did is like, you know, we have this huge monolithic architecture. It's all Ruby on Rails. It's a temporally sharded MySQL. We have Memcached. And at the time, we had about 60 employees, about 60 engineers in 2010. So it's a relatively small group. And each engineer, for the amount of people visiting the site, was actually quite large. So the first thing you have to do when you come into a situation like this is you really need to stabilize it and understand what's going on. The thing is that a situation like this is not that common. I mean, we all want to have this kind of load. We all want to be abused this much, but this was actually real users. This is what we wanted to have. So how do you actually move forward? How do you learn and make improvements and not just survive this? How do you actually take this load and actually learn something from it? Because ultimately, we have to improve the system. So, you know, one of the things to talk about is you want to be realistic and ambitious. I mean, the thing is like you need to go into this, you know, as Gene was saying today, with duct tape. in some cases, baling wire. You got to go and fix these things and what you think are probably the worst possible things you can possibly do, but just do them because they'll get you through this. So you're going to stick that mem cache in front of it. You know, that's not the greatest thing in the world, but you'll learn something from it. Can you survive? Can you get past that point? But the real thing you're looking for in this is how do you make the long-term improvements? How do you recognize these patterns such that you can actually improve the entire system, not just that one temporary problem? Because the things you're going to be able to fix right away are going to be, oh, well, this machine isn't working right. This needs a cache in front of it. This needs a better disk buffer. There's a bunch of small improvements you can make, which I call the duct tape, the baling wire. But then you're wanting to look for the things that are really wrong. You want to understand what the fundamental constraints of the system are and what can you do to change those. And so going into the World Cup, a lot of people flip switches. It's like turn on this load, shut off this load. They flip everything at once and then they hope to learn something from it. You don't learn by just randomization in general. You can learn some, but you have to do it in a controlled manner. But you need to actually approach it with, if somebody were to give you this control panel from an airplane and say, okay, flip this one switch, how long would you spend trying to figure out what that switch was? Did it have any effect? You need to understand what you're doing, and a lot of people go down to this approach. They start off with what they've done in the past. They turn off traffic, they shut off the website, but that's not necessarily learning anything. So you want to find a way in this to actually learn. And science, we kind of talk about it. Everybody says scientific method, but the reality is that you have to have a hypothesis and test it. You actually have to go into these situations and say, I think this is going to do something, and here's how I'm going to verify it's going to work. You don't just flip the switch and hope for the best. Sometimes you do. Sometimes, as Gene said, you have a gut feel and you go with it. But that's not always the best way to do it. If you have a way to verify, you try and verify it. Gene would, I'm sure, agree with this, is that they were in that control room always looking for some way to verify what they thought they did actually did the intended consequence. Like, oh, we set this set of instructions, did it actually work, or did it not? And then maybe you retry it. Sounds like that worked for one of their situations, but that's not always a great thing. And kind of set this up is you got to have trustworthy data. So we published a blog post at this URL, I think yesterday or Monday. But basically, we had to reinvent our observability system. We had to figure out how to get enough stats for all the machines we had, for all of the stats we wanted to collect. Normal metrics, we didn't know what they mean. The thing is, you have to know where you're measuring your time. You've got to know where you're measuring the inputs. Because if you don't, you end up making decisions that you really don't know what they mean. So if you're not measuring it and understanding what the Q depth is at the right place, how do you know what that did if you actually make a change? And so I encourage everybody to understand what their data really is versus what you think it is, because we have a lot of bad assumptions here. And then the next part of this is ultimately you got to set expectations, because it's kind of a high-stress period when everything's breaking. You got your CEO yelling at you. You've got the board of directors. You have a lot of angry people. And so you've got to have the right idea of what you're doing in here. So you got to go in with every day. We would go into the games and we would say, here's what we're going to learn from today. Here's the set of steps. Here is the operations manual that we are going to follow. And at this level, we'll do this. At this level, we'll do this. And as everybody has the same game plan, you can actually move forward. If you have people disagreeing on, what steps you're going to try, what, you want for the lesson, you're never going to make progress. And there were some bad ones. We had to make some calls on the fly, but you've got to maintain calm and order. Just like that control room. If everybody's yelling, you're never going to actually come to an agreement. You've got to have some level of control and some idea of hierarchy. And let's also say that a big thing here is postmortems. After these are done, you really need to spend some time understanding what actually happened. Not John Alswa, who I saw earlier today, and I don't think he's in here, will say you've got to trust each other. You can't go into these postmortems and it just be a blame festival. You need to actually have people be honest enough to say that they screwed up, to say that they did this thing and why they did it. You need to understand the human beings in this room in addition to, what systems went wrong. I mean, we all want to blame the, mem cache that failed or the machine that failed, but we've got to understand the humans involved here, and you've got to make it a part of the process. You got to learn. You got to take the lessons that are being offered to you today and actually do something with them, because in general, while we talk about doing good postmortems, I've seen a lot of really bad ones over the years of people who just want to not be blamed. And the thing is, you have to make it a blameless system if you can. And that means all the way up to the management. You can't have managers firing people because they don't like the answer. And that's hard for certain management change to deal with. So be aware of that. And it really is about teamwork. Like, you have to have a culture and a management that allows you to do this. If you're given a problem and you're not given the time and the resources to do it, you're never going to solve it. You're going to end up basically pushing the buttons and just satisfying a checkbox. You're not actually going to learn anything. So you have to have the right culture that allows you to learn and actually make improvements from it. Because most systems are, you've got to, if you know what it is, we wouldn't be doing it. The thing is like, in general, the things that Twitter and everybody else is dealing with, we're pushing the boundaries at the time. Like, people will say, oh, it's an easy problem. But if it was an easy problem, why isn't anybody else doing it? And that's generally where culture comes in. You've got to have the culture that says, let's explore. Twitter was very much in its early days about how do we explore the largest number of possibilities? How do we be the most flexible about the design, quick iterations? And at some point, we realized that, and it was ultimately in 2010, that reliability becomes part of this. So, and the other part you have to talk about this is like, capacity planning and forecasting sounds nice, we all need to do it, but how many of us really understand what our capacity is? How many of us really understand what that means? Twitter had an idea. We were wrong in many places. We actually would go into it. I remember at one point having to go to the CEO and say, yeah, we don't have the machines to do that. That feature you want to turn on? No, can't do it. And that's a hard thing to do. You've got to have some ability to do that. But you have to be realistic. You can't just double, triple the size. That's expensive. Are you really going to use it? That's burn rate on your startup. You don't want that. So you've got to be realistic about it. You don't just go into it saying, hey, I need an infinitely large data center because I might need it. Anybody who hears that is just going to laugh you out of the room. And so you've got to be realistic. You've got to figure out what a real buffer is. What do you expect to use versus what is available? I mean, a lot of it is understanding what the software, what the developers are saying, and also, having some gut feel for this because there's a lot of margins on it. And then next thing you have to think about is, as I said earlier, these longer term challenges and changes. Like, what do you need to change in the system to fundamentally make it scale to past the point it's at today? In general, people are very good at telling you, their margins on the existing system, but recognizing what the real bottleneck in the system is early enough so that you can actually do something about it is actually one of these critical parts about changing the system. Like, you actually have to recognize, hey, this mem cache that we love so much is actually causing us problems. It bought us a bunch of read capacity, but now it's causing write problems. Like, how do we keep them in sync? How do we, deal with the inconsistencies of a mem cache coming and going? You get very interesting race conditions when you have mem caches that get net splits. So you're writing to this mem cache, it's suddenly gone, and then it comes back and it's got old data. So your system that's, giving you all this read capacity is now out of date, and you don't know that. And so you've got to design that into your system. Memcache is very powerful, but it has certain conditions like this that will bite you. Can you recognize that your MySQL database, one of our lessons was that our MySQL database was fundamentally being limited by the amount of IDs we were generating on it. We physically could not generate more than 3,200 IDs a second before we actually ended up flushing buffers to disk and basically paused the world while it flushed those buffers. That was bad. It's gotten better in MySQL, But at some point, you need to know that you can't go past this. And that was one of those lessons we learned in the World Cup. So, you've got this system. You're trying to, duct tape and baling wire, reassemble this. You're learning these lessons, but nothing that's worth doing in software can be done in a few days. I mean, if by the time you have a discussion about it, by the time you write up a simple design, by the time you code it, by the time you test it, you put some real load on it, you put some real users, you're usually talking, insanely probably a month. And that's, if all said and done. In reality, it's probably 6 or 9 months because there's going to be delays, there's going to be hiccups. So you got to be thinking of, when I say longer term changes, they're 6 to 9 months. Like, are you going to re-architect the fundamental storage system? Are you going to change what a sequence ID is? You can do some of these in a month, but those are everybody focused on it in a lot of companies. You can't have too many big bets in the air at the same time. And so we, at the time, started a bunch of changes. So a blog post that we recently wrote basically talks about some of these, where we moved from mostly Rails and Ruby to Scala and the JVM. The reality of why we did this is that we were doing about 200 to 300 requests per second per server, and suddenly we were doing 10 to 20,000 requests per second on the same hardware. So when you're dealing with hundreds of thousands of requests per second, that is a lot of hardware. And we went from a single process per request to finagle, and we'll talk a little bit about finagle, but the big thing about this is it allows us to do way more things in parallel. Twitter's fundamental scalability bottleneck was by using Ruby, we had a single process doing every request. So if that request was tied up doing something, it was not available to anything else. Ruby has a relatively large overhead per process to run, and so all of our machines were basically memory limited by what we could do. We had to run n number of unicorns on this particular set of hardware, and that was all the slots available for Twitter. So if one request got slow, if somebody didn't set a timeout properly, if somebody didn't do retries properly, we could effectively lock every unicorn in the system up. A lot of our original whales were over capacity from this very issue, that our Ruby instances were all busy doing something. And we did learn a lot by cleaning that up. And one of the things I'll say that we learned during this period is to put deadline times. Recognize that you don't know down in the lowest layer of some multi-tiered architecture what an appropriate timeout is. You don't know what time that request came into the system. Between the load balancers, the Nginx's, the Apaches, go into the front layer, you go into the back end, you go into the database, what's the appropriate timeout to set? So if instead you set a deadline time up front and say, hey, we're going to exit this at 5 seconds or 10 seconds after it shows up, then if that final time is known, that bottom layer can actually make a decision and reason about it differently than if you say, oh, I have 200 milliseconds. Well, 200 milliseconds times what parallelization, times how many sequential calls, it allows you to reason about it better. If you have no ability to satisfy that request, don't try. And that's one of those major lessons we learned during the World Cup, because we discovered that pretty much we were dead during some of these games, and we were like, what's going on? Well, what we discovered was that Apache, by running strace, was basically getting these requests to write to a socket that was already closed. We're like, what? And so we actually traced it in, and we discovered that Apache had basically decided that based on our timeout that we'd put in for overload protection was exiting, but the unicorn underneath was actually doing work on that item because it had gotten it off before Apache shut it down, but was actually useless work because you go to write it to the socket and it's already closed. So you just wasted a bunch of time for no reason. So we actually put in a deadline time that said if we're within a certain percentage of that final time, don't even do the computation. It's pretty much a relief valve in the system, and that allowed us to recover faster. So we went from a period where these spikes would beat us up for a long period to a period where that spike actually quickly dissipated. And that actually really helped on the whales. The other thing we changed a lot during this time, and this is actually more of a company thing, is we had to re-architect the system. we had to go from a single monolithic process that we internally refer to as the monorail because it was this monolithic Rails application. Very hard to change it. All these engineers are in the same code base. The side effects of that were becoming painful. And what we changed to is a service orientation where we actually have core nouns and verbs. So things like we have a tweet store now, we have a user store, we have services on top of them that deal with all of the modifications. So you can start to reason about it. You can say, hey, a user modification goes through here, who needs to be notified of that? It's one place. It's not, in 20 different files spread around your code base. And so that allows us to move faster. So our teams can now be independent. Our tweet team can now really own the tweet problem. Our user team can really own the user problem. Our service, the graphs service can really own the user graph. Like, what is the interactions? And deal with the problems that exists, especially when you get into multiple data centers. How do you synchronize? How do you make sure that those changes are being, synced around all of these different data centers? And then one of the big things we did, and this is something that as an industry we don't talk about much, at some point you have to move out of that public cloud. At some point the cost of running in that public cloud is prohibitive. As a company, you're going to be limited because you can't get the number of machines you need to scale up your business. You want to have control over as many systems as you can, and it's not to say AWS and all these others are bad, but at some point it just becomes impossible to run in those clouds without getting a lot of support from them. Like, we made a discovery during one of our outages that we had overloaded a core router in a system that we didn't even know existed. Like, we were in a cloud, suddenly we're seeing packet losses, and we had to shut down our Hadoop processing during the World Cup because we had overloaded the data center, completely and utterly overloaded it. Like, that switch was dead. And it was to a room that we didn't know existed. Like, going back and figuring that out was painful. We had a lot of help from the vendor, but at the time, it's like we own the failure. We actually had to fix the failure. You can't blame the vendor. You can't blame anybody. It's your own problem. So we actually had to move out of the public cloud into a managed system, and that transition is actually something that most companies don't talk about. That transition from, you're going from having a public cloud where you don't have to think about provisioning machines, you don't have to think about anything, and suddenly you get to this point where everything is your problem. Like, how do you start up a machine? How do you bootstrap it? How do you know which machines you have in your data center? How do you, logically think about what machines are available? What's the availability of them? And that is actually a very hard problem. It is not something we talk about. We need, as an industry, to actually start doing this more often. Like, what is the criteria to get out of AWS? When does it hit that point in your architecture where it no longer makes sense? For many people, that may be never. But if you're getting into hundreds of thousands of requests a second, you probably need to have a conversation with people because that's a very expensive data center. And so, we now start talking about as a data center as a failure domain. We don't want our single data center to ultimately be able to take down Twitter. You want to be able to have a natural disaster, the Godzilla event as we'll refer to it, and that Godzilla shouldn't be able to take out your whole system. You should be spread out enough. Your data should be in a place where you can have multiple data centers so that you can survive these Godzilla events. And the other thing is that we have started in open source this project called Mesos, which actually simplifies this some. Rather than having a bunch of different machine configurations and every machine is a special snowflake, you end up basically making one pool of machines and having a resource manager on top of it that schedules the jobs to where the resources are available, and that is Mesos. Mesos is really about going from having to reconfigure machines to move them between roles, having all these special machines, these special types, to basically just talking about resources. You want to talk about how much disk do I need, how much memory do I need, how much bandwidth do I need, and Mesos allows that. And it's very good at rescheduling jobs, having shards moving around, and it expects failures. So you've got to re-architect things slightly different because persistent disk storage in this is not as easy. And so you've got to rethink some of the things, but it provides you way more flexibility to use your machines. You don't have this cache that's completely memory bound with no CPU and no disk. You basically can intermix your workload, so your machines aren't as specialized. It gives you a lot of flexibility. Like I said, some problems, you got to deal with that. The other part about this is what I refer to as dynamic configuration. You don't want to basically make your entire system basically locked down on your deploy. If you have to do a new deploy and get that out to every machine in production, you don't want that to take down your system. You don't want that deploy the first time it hits to actually be your problem. So we've actually, and Facebook has this, and Etsy has a similar concept, Google has this concept. We actually push the code out live, but off, and then we have a configuration mode where we can turn on that code. We can actually basically turn that as a dial effectively on every machine in production and say this thing is now live for 5% of users, 10%, 20, 30. You can do it at very small increments, but we can now turn things on and actually watch them with real traffic versus simulations. And we do run the simulations. Everybody has to do this. You find a lot of things there, but real traffic exposes things that we did not, as engineers, think were going to happen. There's the unknown unknowns. Well, running real traffic, you find those really quick. If you try and run those without that, you're going to end up saying, well, this is 100% going to work. You start turning it on, and you overload some other system you didn't know about. There's unintended consequences every time you do it. So the ability to turn this on in increments, look and make sure that everything's stable as you do it, gives you a lot more flexibility. You don't have to be afraid of that deploy. There are times, and they're nastier, where you have to do that, roll forward, which is, oh, I changed the whole cache ring. And how do I change that without, a new deploy? Those are messy. Those are the last resort in many cases. But you need to, ultimately the ability to quickly change your configuration at runtime allows you way more flexibility. We now have a process where we can actually tap compare traffic between the old and the new system and verify that that is actually correct before we turn on real traffic to it and switch it to that new system without a new deploy. We'll then do a deploy afterwards to reset the default so that, if there's a failure, it won't go back to the old default, but that's at the end, and that's easily managed. It's just making sure to, dot the I's and cross the T's kind of level. And the thing that gives you is way more flexibility. If you're not actually trying to say every deploy has to be perfect, every deploy can't cause a problem, you get into the state where you're testing it just to make sure it's good, you roll it out as fast as you can, but the really risky parts of that deploy aren't, it's just making sure that deploy got to all the machines. It's making sure that everything looks right. You're not worrying about, well, did this brand new chunk of code do something I didn't know, and how do I phase this onto thousands of hosts without, having the users see partial results? And that's way more important than, getting that code out. It requires a little more configuration, but we've done this on machines. Doing it in your data center gives you flexibility. So another thing we had to do was ultimately improve our storage. The thing is storage, everybody talks about, the latest solution. The big thing we ran into was that we use MySQL for storage in many situations, and we actually, in trying to write the number of tweets per second, we're overloading. So we had temporally sharded MySQL, which means that one set of tweets for this period of time was on one set of databases, a master and a bunch of slaves. That master could not write fast enough. The slaves could not keep up with it. So we went to the system that we designed called Gizzard, which is a sharding mechanism on top of MySQL. Still MySQL on the bottom layer, but it's sharded. We can actually have lots of shards and move them around, have the infrastructure to actually deal with that, because we need to be able to move the service around, move the shards around as users become popular, as break them down, so have a hash ring effectively that you can change. Gizzard provided us that ability. We also had to improve Memcache. We've open sourced it, and now the main Memcache tree has the same change, slightly different, but we created a thing called Twimcache because we discovered during the World Cup that Memcache has this lovely characteristic we had decided to reduce the number of timelines we stored. Like, number of tweets in a single timeline, we're like, well, it was something like 3,200, let's have that. Just, it's not the real answer, but let's just say that, it's just 1,600. So that's half the memory. You can store twice as many timelines in your cache. Isn't this a great idea? Well, the fundamental problem we ran into when we did that is Memcache has this thing called slab calcification. Well, we refer to it as slab calcification, which basically says that if you change the size of your keys, Memcache doesn't actually reallocate the memory. It's fixed from when it started up. So whatever key size you were actually storing, that's fixed until you restart the process. And so we went from having, say, 1 megabyte keys to suddenly having half meg. That's a great thing. Well, there's no slab for these half meg. Oops, what the? So we had no key for this half meg key, or no space for this, and basically Memcache is throwing it out. It's like, I don't have any room, I'll throw it out. And it's kicking out the old one because it's like, oh, that's no good. So suddenly we had no timelines in cache at all. And we had to bootstrap all of Twitter over a night, and let's just say that was one of the most painful nights at Twitter. And since then, we've learned that you actually have to have a little better memory allocation. So we did end up putting a better memory allocator in there so that you can resize these slabs without restarting everything. We also now have more of a storage as a service solution. You don't want every group rethinking their storage. You don't want every group saying, oh, I'm going to create my own key value store. It's great. It allows you to iterate really fast. It makes a nightmare for your operations team, your reliability folks, because now they have to know every different system under the sun. You don't want to support that. You want to allow iteration, but you've got to allow things to win. I mean, I've had this conversation with a few different VPs over the years, and ultimately the great thing about genetic algorithms and letting things compete against each other is you actually have to have a limit that they're fighting over. You have to have some constraint. If you don't have that constraint, be it machine resources or people, you end up with just a disaster. Like, you end up with people that are burnt out because they can't learn all the systems. You end up with machines that are not tailored properly. So really learning, coming down to a few set of technologies that you really work well. Snowflake, which was our distributed ID generator, it's open sourced. It allowed us to get past just the sequence ID problem. And now we have these 64-bit IDs, independent of data centers. We can have, a bunch. I'm trying to think what the exact number is. I think it's 64 data centers and 128 or 64 days. I have to look at the numbers. It's been a while, but and each one of them can have like 1,000 machines generating IDs. Each one of them can generate 1,000 per millisecond. So it provides you a little bit of flexibility. So one of the things I've touched on a few times here is development speed. All of what we're doing here is to try and make the development faster. We as startups in this community are all about making systems and development easier for the developers. If it's not easy, they're going to leave. The users aren't going to see anything. They're going to leave. We die. So we have to make it easier to ship but contain that damage. We actually have to figure out how to make our systems resilient, how to make our companies resilient to people leaving. How do we do that? And that's actually been one of the fundamental problems with running any large system is like, how do you allow the developers to move at full speed but not take the system down? And all of Twitter in the last few years, from 2010 on, has been, how do we allow more specialization, more understanding of that whole system so you can actually improve it? And so that's, going a little faster than I thought. So, one of the things I'll say is, like, we consider the fail whale now an endangered species. It's mostly gone. I won't say it's completely gone. I think anyone who says that they never have a problem is not facing reality. So we'll say it's mostly gone. And then we went from event-driven spikes, continuously pushing the reliability of the system. Now events are trivial for us. So events now, and to give you an example of that, so a few weeks ago, we had the largest tweet spike known, which is 143,000 tweets a second. So during the World Cup, we're seeing 3,200. Previous peak before this was 33,000. We put in a new tweet store. We finally got rid of some of our bottlenecks, and we had 143,000. That was 1 second. When we started at Twitter, 300, I mean, I started back in 2009, the highest peak we saw was 100 something, you know, just to give you an idea of like what we've changed to. And that was, you know, you can see this timeline, everything else is just pales. We're seeing about 5,000 to 6,000 tweets a second on average right now. That spike just nuked it. And, you know, so just to show you, if you change this, if you actually break things down, allow better separation, allow developers to move faster, go to technologies that give you a little more flexibility. So, you know, Ruby is not a bad language, and it wasn't the wrong choice, honestly, for Twitter early on, because we wanted to iterate really fast on the design. We wanted to iterate really fast on things that, honestly, were really boring to most systems engineers at the time. It's like, we want to quickly change the page. We want to change the layout. Ruby and Rails allowed a lot of flexibility there and allowed a lot of rapid iteration. And until we had a high enough number of users hitting the system, until we had latency problems, until we had machine, you know, crunches, it was better to actually let the developers go as fast as they could, which in the language they knew. But at some point we had to transition. We had to take this system that was known for being Ruby and transition it off. It took longer than any of us would have liked. I think the thing you need to realize is a large-scale architectural change hurts. And you've got to support both systems while you do it. So you actually have to have your system designed to have enough capacity to run both simultaneously, which, you know, the executives are not exactly fond of hearing that, but you fundamentally can't change what a machine can do. And so you've got to figure out ways to test this live. You've got to figure out how to switch it. And then the other thing I'm going to say is, like, this is a marathon, not a sprint. Most people who get into, you know, the mission control type situations or running this kind of stuff burn out. They assume that it's just this one thing, I'm going to survive for the night, and then I can sleep. Well, who's going to do it tomorrow, especially in a small company? If you're basically comatose by, you know, 1 a.m., 2 a.m., who's going to pick it up when it fails again at 3 a.m.? Who's going to hand off to? We don't have the, you know, spare teams that Gene was talking about coming in and like taking over for you in general. We don't have enough people. So you've got to figure out how to keep doing mini marathons and recover quickly. You've got to figure out how to do this because, you know, it is a messy thing. And yeah, as I would say, Endangered is the fail whale. That's my boat, and it's much smoother sailing now. It's not being hit by whales. And now I'm going to open it up for some questions. If anybody has any, and a couple links. There's a link to the new TPS record and the observability thing we just published this week. We will be publishing more blog posts in the next few months about these changes. It's a lot, kind of high-level overview here. We're going to publish a lot more detail about these changes, but is there anything I can answer? Whoa, and do we have any mics or anything?
No handheld mics.
Okay.
Please speak up.
And I will try and repeat. Go ahead.
What made you guys move to Scala as what other things did you evaluate?
We evaluated a lot of things. We tried to get, so the question was what made us go to Scala? And the reality is that we made the decision to go to the JVM, and Scala was the most natural fit for the Ruby developers and the functional programmers that we had at the time. It caused us a lot of pain. We had to write a lot of core libraries that were not available. Finagle, we've had to deal with things with Netty and making it work. We've had to put in all sorts of translation, translate our Git Macaw type, or the Swift rendering framework into it. We've had a bunch of challenges from it. It really comes down to we wanted to get in the JVM because the performance we were seeing out of Ruby, especially not being able to use concurrency primitives, was killing us. We fundamentally knew we needed to get to a parallel framework. We needed to have event frameworks in Ruby would have worked, but at the time they were not as mature. The Ruby VM is not as good about garbage collection as the JVM has gotten to at this point, and we needed the performance. We fundamentally ran some bake-offs between Ruby, between Java, between Scala. We tried some crazier ones. Alex Payne was there at the time and was encouraging even crazier ideas. But at the time, we wanted to get, I mean, it really was the VM, and we needed the garbage collection. So.
Yeah, I'm assuming you successfully managed to migrate to a data center and all the specialization that requires in growth. It's pretty easy with a small team of generalists to use the cloud, but once you start talking about CCIEs and SAN engineers, it becomes a lot messier.
It is true. That was actually I led the project, so I know way too many details of this one, but I will tell you that fundamentally it comes down to you actually, I mean, it's a very expensive thing to bring up a data center. And we're not even running our own data center. Like, we are actually buying space in a big facility. Actually building and breaking ground on a new building is,
Even just assuming physical rack,
yeah.
a few racks, that's still hard.
It is hard. You've got to hire the NetEng folks. You got to hire the power folks. You got to hire, you know, all these people that understand systems that you honestly have no clue about. That was actually one of the messiest transitions we've ever done. And luckily, we were able to do it and post a blog after saying, we moved data centers. Hope you didn't notice. Which is kind of fun, but I don't want to do that one again. That was a lot of gray hairs. Yeah, go ahead.
I can look this up, the Wi-Fi is so slow, but how heterogeneous can the hardware be on Memphis?
It doesn't have to be heterogeneous. We can have different hardware, so they'll have different RAM, different CPUs. You specify how many cores you need. So the scheduler deals with most of that for you. And there is still improvements going on to it. For those who have ever dealt with Google, you'll hear this term called Borg. This is effectively our equivalent of Borg. So that's, yeah, it allows you a lot of flexibility. It's not perfect yet. We're still improving it, but it is way better. There's now a bunch of open source companies forming around this technology. So go ahead.
Do you guys allow teams that run individual services to make their own like technology choices, or is it all like ubiquitously the same framework, all Scala? Is there much
So when I say Scala, let's just say we still have Ruby in the stack. We have Go in the stack. We have, to say that we have a large number of technologies in Twitter is putting it nicely. Some of us have had this discussion of trying to limit that, but you really can't. You want to allow the engineers to iterate as fast as they can. And sometimes those decisions will make you kind of uncomfortable as an engineer, as an architect, as a, you know, somebody who's been around for a while, but you have to accept those. You have to accept people iterating. And as I said earlier, you've got to have a constraint though. You've got to make it so that you don't just allow this infinite reach. If they're going to do that, they need to possibly have a higher, you know, on-call schedule. They need to, you know, run it more themselves because you can't expect your SRE team to own that. So you got to actually put some constraints on it that make it not the easiest way to do it. And that is something we struggle with, and I would say every company struggles with, but you don't want to stop the engineers. You don't want to stop the good ideas. You want to make it as flexible as you can. So, any other questions? Go ahead.
Did you, were you able to write your aquatics to be able to tweet to the auto helm here?
No, I haven't been able to tweet to the auto helm yet, but I could. I need to fix the boat back up to get it back sailing after too many years of being deep in Twitter, and I'm sailing on friends' boats right now, so I haven't done anything with the autopilot, no. Go ahead.
Can you talk a little bit about your operational learning?
I'm asking for the UV person.
Operational learning procedures.
So when failures start to happen, what types of tools you use across the company to actually identify cascading failures or?
Well, the big thing, and this is actually something as an industry, I feel like we have some improvements we can do. We have dashboards. So I showed you a dashboard. If you go to our blog on the observability, you can see a bunch of dashboards. We have primary dashboards, and we have screens that people are watching, and there's ones that are generally the overview that everybody knows, and we keep those up to date, but those are human-driven right now. And I've learned that over the years, as new systems come online, new engineers, new dependencies are growing all the time. Our systems are an organism that's growing. If you have a large-scale distributed system, enough engineers, things are changing that you have no idea they're changing, and no operations SRE can actually keep up with it all. And you need to start being more organic about it. You need to start learning these things naturally instead of after the fact. Right now, I would argue almost every company learns these things after problems start occurring. And we have learned a lot over the years, but I think there's a lot of opportunities here about recognizing emergent patterns in dashboards and graphs that we don't see today. And so, yes, it's still a work in progress. Okay, yeah, one more. Go ahead.
So you talked about having multiple infrastructures at the same time and supporting both. How do you migrate from the old one to the new one, especially when you talk about changing your storage services and things like that?
We have to write both. We actually, for a while with the tweet store, we actually were running them simultaneously. And at some point we switched the top layer to say which one's getting the real write. So which one are you reading from? This becomes the question. So you can write simultaneously, that's not a problem. But then you have to start putting the read load on them and actually verifying that they're consistent. You're doing that as a dark traffic initially, and then you put it on for real, and then turn down the other one. But you're still running, when we switched to MySQL, or off of just the plain MySQL shards, we still ran them for 6 to 8 weeks afterwards to make sure that the new system didn't blow up in the meantime. I mean, that's just the thing, is like you're running it, you can't just say, oh, I turned the switch, it's all done, go have a party. It's like you have the party, but you still have to run that old system for months, weeks, to make sure that it's actually not going to cause you a new problem. You want to have that backup. You want to have the ability to say, hey, this failed, let's move forward. So I think we're done with questions, and I thank you for your time. And